You can use this. Just do it, everyone. It's fine. Just one more.
Oh, yeah.
Yeah, so I'll give you the 3 minutes, around 10 minutes.
Oh, yeah.
Great. So I'm just going to make one quick comment just to say welcome back.
Go ahead.
Okay, welcome back everybody to the afternoon session on AI and atmosphere, ocean, climate. So the first speaker for our afternoon session, I think we have 6 all in person this afternoon. So our first speaker is Yanping Li, who's going to be talking about convection permitting climate modeling.
Yeah. Thank you. I'm Yanping Li. So in this talk, I'm gonna take the opportunity to summarize the work my group have been doing for the last several years. That is using the convection permitting model, which large scale, like continental scale, to work on climate adaptation study, mainly focused on 2 aspects: the agriculture and the wetland. So let's introduce a little bit background. We know, like, we are in the era of climate change, right? And the IPCC report give us how the Earth's atmosphere is going to be like in the future. So you see that here, and I mean, this is a famous IPCC AFI report, the figure we adopt from. So in the future, it could be the scenario, like 3 major scenarios. Like the future could be, as worse as we could imagine, like with the same CO2 emission as current level. That's the RCP 8.5, or try to reduce to carbon. Reduce the emission and maintain it to be current level, or do something like carbon neutralization to reduce the concentration. But anyway, this scenario, CO2 emission, CO2 concentration is used as a part of the forcing, like radiative forcing, to drive the GCM model, then which gives us the like meteorology variables from the GCM, right? That's the foundation for our climate adaptation study. Like the GCM output gives us how the future is going to be like, but at a closer resolution, which is about like 100 kilometers. So for us, like, we want to do climate adaptation. It's usually in a local scale, right? Like local farmers and like environmental policy, whatever, they need a detailed information. So we need to do something to convert or translate the IPCC report to some local scales. And what we can do is there's several popular approach, like statistical downscaling, which is kind of used a lot 10 years ago, maybe. And then later we start to use a lot of dynamic downscaling, like which is, you can see, like GCM covers the whole Earth, and we use a small domain that covers the region we're interested in, but with more like fine resolution. And we put it, we net it to the GCM and use the GCM GCM output at grid point and use it as a boundary condition to force the regional climate model, and then we get like information at much finer scale, but smaller region. And by doing that, we are able to see details, right? Local details, the mountains, lakes, and rivers, whatever. And this is then used as the regional climate assessment for the future impacts. Okay, so the fine resolution model we used, it's a 4 kilometer regional climate model. And why we call it convection permitting in my title as convection permitting is because convection usually happen in a fine scale. You see, we put a cloud there, right? If it's GCM, it's inside of a grid point, so you can the model cannot actually see it. But with a fine resolution, you can see that the red and lines here, you can see that it's in several grid points, so it's able to simulate. The model is able to simulate it physically, and without seeing it, we have to do some parameterization. It's like a statistical relation relate to the precipitation or the cloud to some meteorology variables near it, which is not so precise, and it could be a major source of errors. And but with fine resolution, what we can do is we can improve the simulation of the precipitation, especially like diurnal cycle or the 24-hour cycle, and which is important at some regions like coastal regions, and also the timing of the convection, and also the extreme events, right? And in addition to that, with fine resolution, we have better land surface representation, and for that we are able to represent the complex terrain and the surface heterogeneity. Okay. So give a brief introduction about the model we used. It's a weather research and forecast model. It's a US model, and it's a community-based model and open source. And also the model is kind of highly modularized by like testing or selecting or like optimizing different schemes, like a cumulus, like in cumulus scheme you have several options, and the boundary layer scheme you have several options, and radiation, like long wave, short wave radiation, and whatever. Like you select different combinations, and then you can easily adopt the model to climate region you are interested in. And also for the future climate simulation, we use the technology called the pseudo global warming. So let me introduce a little bit of what is pseudo global warming. We know, like for GCM, if we want to simulate the future, the end of the 21st century, we have to do a central long simulation, continuous simulation, integration. But it's, I mean, for the middle part, maybe may not be interesting. We want to see how the future, the end of the century, is going to be like. So what do we? The technology we used here, the pseudo global warming, is like we don't need to simulate the part in the middle. We just simulate at the end of the century, and compare it with the current climate to see how the change is like. By doing that, we save the simulation time, right? And we reduce the number of years we're going to simulate. We can use this resource to expand the domain, and we can also increase the resolution. And the chart flow tells us how to do the simulation. For the current simulation, it's like a dynamic downscaling. We just use EI interim to force the 4 kilometer wave and simulate, regenerate the historical condition, right? And for the future climate simulation, we select 19 good GCM, and we averaged their monthly output. So it's kind of ensemble mean of these 19 models, and we subtract the future with the historical, and then get the delta, which we call it climate perturbation. And this delta is monthly, like climate increment, right? And then we interpret it to every 6 hours and add it back to the EIA interim, and use it as a new forcing to force the wave. And by that, we're able to simulate some. Okay, so yeah, so I keep going and you fix the technical problem. So with this technology, we completed the Western Canada simulation. That's one simulation we finished, which is for the AC being used for GWF. And also we work together with National Center for Atmospheric Research at NCA. That simulation covers the whole US and the southern part of Canada till Jasper, I remember. And next, okay. So I'm talking about the lower left, the CONUS 1 simulation that covers whole US and the south part of Canada. And then like we later worked together with NCA on the other project called CONUS 2, which has a much larger domain, cover the whole Canada, that's the polar part of Canada. And also the forcing is a little bit different. And now it includes the movement, the northward shift of the storm track. So CONUS 2 and CONUS 1, they are not just the domain coverage, but also a little bit different in the physics part. Okay, so those are finished. And then based on that, we started our climate adaptation study, and like we still use this coupled high resolution continental scale regional climate model as our foundation. And in addition to that, we developed the additional crop module, like the dynamic crop module that include different crop type. And also we coupled it to the coupled land atmosphere model and use it for like crop year simulation, crop strategy, and also future crop choices for our region and the irrigation, the efficiency of the irrigation. I mean, a lot of discussion based on that. And on the other side, we also did some model development, which is the wetland module. Like we know our region, like the prairie has a lot of wetland. So with this new wetland module included, we are able to study how the climate change impact on the wetland distribution, and also how this the change of the distribution is going to affect the waterfowl population, the knowledge that the ecologists are interested in. And also combined together, we can see the possible on-farm benefits of wetland retention and restoration. Okay. And why? And I mean, this is our motivation, because like I know when you flew to, I mean, from Vancouver or from east to Saskatoon, you see the land, right? The land is a lot. There's a lot of pond, like which is the periportal regions, and that's the motivation we decide to split our study paths to two independent paths and join together by the end, right? And also like we work I mean, for the agriculture part, we work together with the experts on the development of the module. And now it has I mean, used to have a corn and soybean, and in Canada we included wheat, and in the future we hope we can do canola. Okay, so with this model, we are able to look at, I mean, our model, the unique part compared with agrocrop and other models, the unique part is like the meteorology forcing is entered dynamically like every 6 hours. So we are able to simulate the crop fail caused by disasters like extreme flooding or something like other model cannot do, right? And we have that's by doing that we have better simulation of the crop yield, and we are able to do studies like the efficiency of the irrigation or the water use efficiency. Like water, it's not like the more water you put in, the better. It's like it's gonna reach the some margin, right? Like somehow when you put more water later on, it becomes less efficient. And with this model, we are able to do that. And also, so for the wetland module, like like red line is irregular, and sometimes it's even it's much smaller than 4 kilometer size, like it could be hundreds of meters. And we include parameter called F-wet in the model, and like this is a function of maybe as many soil water content, and we like this is more like how we did the parameterization. So we introduced we introduced a definition, and then we put it in the model, and then to use model to simulate the wetland distribution and compare it with the satellite remote sensing results. Then we go back and modify our like parameterization, and we do this as a loop. It's used to be like statistically, but now we use machine learning to help us to improve our like definition of the wetland in the model, which is quite successful. And then we use it to look at how the wetland distribution is going to be like in the future, and which part is more vulnerable, and whether we should take some action now to protect it. Okay, and so with this module, with this powerful platform, coupled modeling platform, we are able to look at the climate adaptation and look at the future, like how much to what extent water determines the crop yield, and the water, where the water will be found from, and better improve the Earth system model, something like that. Okay, and also like back to the Perry, we then be able to combine these two modules and look at the possible benefit of wetland retention and restoration. So I'm gonna skip the city part, and I will jump to the conclusion. Thank you. Yeah.
We have time for one quick question, if anyone has a question. Yeah, you mind using the mic, please?
Thank you very much. That was really inspiring. So for your WRF model, are you planning to repeat the similar work for using SSP kind of scenario models?
But it's going to be a lot of effort. So we will like make a serious decision. Like if a lot of our collaborators are really interesting, and we can combine together and maybe design a simulation that covers most of the interest of the people in Canada. Yeah.
Thank you very much.
Our next speaker is going to be Julie Corot, who's going to be talking about Clausius-Clapeyron and formed deep learning. Very interesting. Are you or people?
It's a PDF.
Here we go.
Can I point with that? Oh, that's great. And I changed it on. No? And then I will be able to change the slides.
I think you should be able to. You just try this forward and backward.
Next. So hold on. That's next. Okay. And then back. Okay, great. Thank you. Hi, everyone. So my name is Julie Corot. I'm a professor at Polytechnique. I'm replacing Pierre-Louis. He was supposed to present, so that's why the title is a little bit different. Whoops. So Mariam and Pierre-Louis are two graduate students that I'm co-supervising with Youssef at Polytechnique. Okay, so thanks to the previous speaker, I'm going to be very quick on the motivation of my talk. So glad we know climate change is established now, and it affects not only the global temperature, but it also affects meteorological hazards. These are water-related meteorological hazards in Canada. In particular, whoops, sorry, I'm going to get this one right at some point. On the southern part, we have hazards related to flooding. And to face these, we need adaptation measures. This is a slide I took from the RISC network, and this network is dedicated for adaptation measures, in particular against flood. But we also need high-resolution data, like it was mentioned in the previous talk, to develop those local adaptation measure. And I'm going to be working with an ensemble. We need ensemble in order to take into account several sources of uncertainty. So this is the CLIMAX project. It relies on a large ensemble LE of the Canadian global model, which has a resolution of 310 kilometers, and there are 50 members. And these are dynamically downscaled with the Canadian regional model at the resolution of 12 kilometers, focusing on 2 regions, Europe and Quebec. But this data is very highly computationally intensive. This has been said in a couple of talks already. And for this, we need climate emulators that are, just to make it quick, they are reduced complexity model that allow to reproduce a subset of the variables of the climate models. But here in this work, we will focus on an emulator which aims to perform statistical downscaling in order to mimic the dynamical downscaling that has been described in the earlier talk. So we start from this low resolution grid, and we try to recover information on a smaller region and on a high resolution grid. So that's going to be our goal. Okay, now more about the data that we use. The high resolution grid has a spacing of 0.11 degrees, about 12 degrees. We have a domain in North America. I'm going to show it in the next slide. The grid that we have has 128 pixel by 128 pixel. And we constructed our own low resolution data. I will explain how in a second. And for the same domain, we have 8 low resolution grid cell by 8 low resolution grid cell. So it's a scale factor of 16, which is pretty close to the one used between the global climate model and the original climate model. I said there are 50 members in CLIMAX. We use only one for now. And we have some data, 30 years of data for training. Part of it is used for validation and a few data for the test sets. So for now, we limit ourselves to 2005 because we don't want to have the climate change signal coming in too strongly. Okay, so now you can see the domain. So like I said, okay, we look at 3 hydrometeorological variables. On the first row, you have precipitation. Then you have a minimum air temperature and maximum air temperature. These are on the same color scale, and it's a daily scale. And we have the interannual seasonal mean. So this is from the winter, spring, summer, and fall. So you can see the 3 variables and the domain, 128 by 128. So now I'll dive into the methodology. First of all, we wanted to ensure physical consistencies. Our 3 variables have constraint. We can think of them as being in a constraint space. So precipitation has to be greater or equal to 0. Tmax has to be greater or equal to Tmin. And we make a mapping to an unconstrained space in order to preserve these constraints. Basically, precipitation is going to be seen as this is a soft plus transformation. We're going to work with prec star here. Prec star is not constrained. When it becomes very large, this cancels out basically, and precipitation is equal to prec star. And if prec star is very large, but on the negative side, this term will cancel, and we have log 1, so precipitation is 0. So this is the first mapping. And the other one, we're going to be working with delta, which is the difference between Tmax and Tmin. And also delta will be forced to be positive. So basically, we make this transformation from our original variables to these. And then when we simulate, we transform back. Okay, some more methodological details. We are in a perfect upscaling setup. This means that our low resolution data is constructed by averaging the high resolution data on the low resolution data grid. Exactly. It's not a completely realistic case. In a completely realistic case, we would work with the global climate model data, and it would not be the exact average. So we didn't want to deal with that for now. And also, we're going to be working with residuals. So by that, we mean that we take the high resolution data and we subtract the low resolution data that has been interpolated onto the high resolution grid. Okay, so this way we can think of working with the details that were not captured by the low resolution data. Okay, so this is a summary that my students put together of the training framework. We start with the high resolution and constrained data. This is really what we want to obtain. We transform them to an unconstrained space, and then we construct our low resolution data by averaging. we make the difference between these two guys, we obtain their details or residuals. And 28 by 128, that's the spatial dimension of my grid. And I have 3 channels that we say in computer science, but these corresponds to the 3 hydrometeorological variables. So I won't go into details of the architectures. We have 3 levels, which is fairly standard with skip connections and convolutional operation to downscale and to upscale. But what's important to keep in mind is that the idea is that as we go down into the levels, the unit will extract spatial features at the beginning, very local ones, and then as it goes lower into the unit, it's going to be wider spatial features. And then over here, it reconstructs the output, so it upscales the dimension. Okay. So this unit was originally at 100 million parameters, but we downsized it to 20 million parameters, so it's still a big model. Now for the probabilistic unit, it has 2 steps. One of them is the training step, and the inference step is a little bit different. You will understand quickly why. If you look at this part of the slide, it's the same that I've shown you before. I have my input, the unit, and my output. And one component of the loss is the MAE, mean absolute error, between the prediction and the ground truth. But then in addition, I have these 2 networks. There are 2 encoders, actually. I have the prior encoder and the posterior. And the posterior, you won't see it afterwards because we cannot use it. It's guided by the ground truth. So we don't have access to that when we want to do simulation. But the posterior is learning a latent space. So it's learning features by being guided with the ground truth. The encoder, which is called the prior, is doing the same, but it's not guided by the ground truth. So we try to learn a latent space with the prior, which is as close as possible to the one learned by the posterior. So we have a second component in the loss function, which is the Kullback-Leibler distance between these 2 spaces. So these 2 spaces are in fact multivariate Gaussian distribution with a diagonal covariance matrix. That's why you see mu and sigma. These are the parameters of the latent space. Okay, and if we move to the inference now, like I said, we don't have the posterior anymore because it was just there to guide the learning of the prior. And we start with our input, the low resolution data. It enters the unit, but it also enters the prior. And from there, we obtain mu and sigma vectors. And then we can simulate from these multivariate Gaussian distribution. We get a sample here. And then the sample enters the unit at the later levels. And it's combined together, and it generates an image. And I can sample several times from the latent space and generate different images. Okay, some preliminary results, since this is work in progress. First of all, some simulations. So over here, we have, again, precipitation, Tmax, Tmin, and Tmax. These are on the same scales. We have the low resolution, so this is the input to the probabilistic unit. And here it's the target, the high resolution. So remember, we learn the residuals, but then we combine it with the low resolution to obtain the final reconstruction. And here we have 3 simulations from the probabilistic unit. So you can see that there's some variability. It's not as sharp as the high resolution, but still it seems to be realistic. It's a bit smoothed. And similarly for Tmin and Tmax, although we see less the variability for these 2 variables. Okay, some metrics. The students computed several metrics, but I'm just showing one of them, which is quantile MAE for precipitation, Tmin, Tmax. For precipitation, we're focusing on the higher quantiles, whereas for Tmin and Tmax, we look at the whole range. We compare several ways to perform the downscaling. 1NN is 1 nearest neighbor, so just a very rough interpolation. BCSD is widely used. It stands for bias correction spatial disaggregation in the climate community. I insisted on having linear regression as a comparison and we have a deterministic and a probabilistic unit. So the one thing we wanted to see was whether we were doing better than the other alternatives. So this is roughly the case. You can see the lines over here. We are below in terms of error to the alternatives. And the other things that we wanted to see was that whether the probabilistic unit was doing as well as the deterministic unit. So this is even doing a little bit better. And quite surprisingly or unsurprisingly, I'm not sure, linear regression is also doing pretty well for test min and test max. Okay, there are more results to come. First of all, there's hyperparameter tuning in progress, especially for the probabilistic unit. And there's, like I said, a thorough comparisons with many metrics. And in particular, for the probabilistic unit, we are looking at CRPS, and actually we're using it also for training. And we want to compute return levels to see whether we do well or not for extremes, and also to exploit the fact that we have a probabilistic output. And our hope was that the probabilistic unit was able to better reproduce the small scale variability. I think I have another section, but I think I'm going to conclude now because I don't have a lot of time, and like this we can have some questions. That makes sense. Okay, so I'm going to just have a little bit. There's some more work in line with the original title of this session, which was on clausus clapeyron, and they're going to go through that also because the results are really not satisfying right now. And I just want to finish with a bit of advertisement. Okay, there's a PhD position open. It's with my colleague Ali Amili at UBC. We're looking for PhD students, which is at the intersection of statistics, AI. It will involve a lot of programming and with an interest in hydrology. So if you are interested or if you know someone who's interested, please reach out. And that's it for me. And I'm open to questions.
Yeah, a couple minutes for questions. So any questions? Go ahead. You can use like this.
So could you elaborate more on how did you derive the prior and posterior distributions for the model?
I'm not sure.
Could you maybe lean in a little bit closer?
Okay, so could you please elaborate more on how to derive the prior and posteriors?
Between the role between prior and posteriors in the unit?
No, how did you derive the distributions?
Okay, thank you. Well, actually, these are neural networks, but quite rather simple compared to this one. That I'm not sure. So they are called the prior, but it's a neural network. It's an encoder.
Okay, I see.
Both are neural networks.
Are they separate ones from the UNet model, or?
Sorry?
Are they the same UNet model or different ones?
They are different. So we have the UNet model here, which is the same one that I presented in more details. And here, these are different networks.
Okay.
Because they learn a different task.
Gotcha. Thank you.
Thank you.
Any other questions?
Okay.
So I have one quick question, which is, so this work uses statistical techniques to downscale with climate predictions, as opposed to dynamical, which you mentioned also. So could you just maybe give a few comments on sort of what's the gold standard at the moment for downscaling, and is statistical versus dynamical, like how are the statistical results compared to dynamical downscaling, et cetera?
Okay, comparing both approaches?
Yeah.
I'm not sure I have such a big overview over the field. I think many good approaches have been developed for statistical downscaling. I think there are still some things missing, like it's not as sharp. The images are not as sharp in the sense that they don't have local details like dynamical downscaling can produce. So there's still much work in that direction. And also another direction that I like is how to include physics into the model. So it's like a combination of both worlds.
Thank you.
Thank you.
Our next speaker is Majid Bayati, who will be talking about predictions in hydrology. wants to go back and forth.
Okay.
Is this the first slide?
Oh, no, it's not.
This is way further.
Yeah. Good afternoon, everyone. My name is Majid Bayadi. I'm a PhD candidate from UBC, and I'll be presenting my research on physics-informed deep learning approaches to characterize catchment hydrologic functioning. In this research, we're focusing on storage-discharge relationships. Well, it's not a news anymore that climate change is shifting rainfall dynamics, intensity, and frequency. And as a result, streamflow regimes are also changing. And there are some research that also are showing that these shifts also are causing the functioning of catchments to change over time. Like the catchments are changing their priorities for storing and releasing water, and quantifying the sensitivity of catchments in releasing or storing water is something that can provide a big picture regarding how catchments are generally functioning, and can hopefully provide some insight regarding water resources management and climate planning.
Maybe just hold on.
Yeah.
Just hold on for 1 second.
Okay.
Well, take your time.
Yeah. Yeah. This sensitivity is a function that can provide us with some knowledge regarding catchment functioning that is useful for water resources management. Well, storage discharge relationships are easy on paper. So if we consider catchment hydrology as a single bucket conceptual model, we can use the first formula to write the dynamics of a storage over time as a function of inputs and outputs. And inputs would be like precipitation, and outputs like discharge and evapotranspiration. And as a streamflow discharge is a function of storage, especially during like the times that we don't have any precipitation, we can use the second formula from like math, from chain rules, to write the dynamics of a streamflow discharge over time as a function of dynamics of storage over time and sensitivity of discharge to storage. And combining the first two equations, we can have one equation that I call it master equation from now on to refer to that later. So this equation is basically defining the dynamics of a streamflow discharge as a function of inputs and outputs to system, as well as the sensitivity of discharge to a storage. So the purpose is to evaluate dq over ds in this formula, which is what we are looking for. And so dq over ds basically shows the amount of change in streamflow discharge if we change a storage by 1 unit, let's say 1 millimeter of height. Lovely as it looks, but it's hard to compare this value between catchments because the streamflow discharge can be very different from catchment to catchment. So it's very common to normalize this using a streamflow discharge at each time. And this is called sensitivity function, as you may see, and is commonly referred as epsilon in literature review. And this epsilon is something that we are looking to evaluate and compare from catchment to catchment. And I should also mention that existing methods in literature studies, they mostly rely on some predefined functional forms and some basically some predefined functions to evaluate dq over ds that might not be valid in reality. So we want to get rid of all these assumptions and not some predefined functional forms. The study area of this study is, as you see, 17 catchments in Great Britain and North America. And we are going to evaluate this epsilon function, epsilon sensitivity across all of these catchments. And the data that we use are just commonly available data: daily precipitation, temperature, potential evapotranspiration, and some catchment attributes data that also are commonly available across different catchments. And the data that we use are from 1980 to 2018 that were collected by our colleagues. So this is the general framework that shows how we are going to evaluate dq over ds, or sensitivity function, using like what is called differentiable learning, or what we use as deep learning to solve for this solution. So the methodology works in a way that we provide some data that I mentioned, and the deep learning model, which is LSTM here, can transform this data to dq over ds for each time, so that if it's used in the master formula, it can best capture the dynamics of a streamflow as we observe from observational data. So this physical formula basically works as a constraint when we are training this deep learning model. And it's needless to mention that as we are using deep learning, we have to train this model. So to train this model, we use the first 70% of data of each catchment for training and the last 30% for testing. So it would be like 1980 to 2007 for training, and we use the rest of data for testing the model to see how it works. And also I should mention that this equation, as it's common in literature, is exclusively applied to recession periods, where we have more direct and explicit relationships between storage and discharge. Well, after this model is trained, it can be evaluated for each time. If we have like daily data, we can have daily dq over ds. And so potentially even it can be used in ungauged basins, because we have available data on precipitation, temperature, and other required data. And this is the purpose of future of this research, basically. Also, as I mentioned, we normalize this dq/ds that is derived from this formula by q value for each time to be able to compare it better across different catchments. Well, something that always needs to be evaluated is accuracy of models when we are using like data-driven models. So this map basically shows the spatial distribution of test NSC of model for the testing time, which was like 2007 to 2018 for each catchment. As you can see, the median test NSC is around 0.82, and median kg is around 0.87. It's quite well, actually. And on this slide, you can see the average epsilon for each catchment across all flow regimes. So one value for each catchment as average. So what we see in this slide is that there exists a spatial pattern across different catchments. Like we see smaller sensitivity for West Coast catchments in North America, as well as for Great Britain. But we see some larger sensitivities across arid regions, especially central regions of North America. So what is interesting here is to decode what is the spatial relationship that we have here. To understand the patterns that we have across different catchments, on this slide, you can see on y-axis the epsilon function, and x-axis aridity, mean slope, and snow fraction of all the catchments that we have across in this study. And what we see here, as also is supported by Spearman correlation values that you see, is that sensitivity of catchments, basically sensitivity of a streamflow discharge to storage, increases with higher aridity, lower slopes, and less snow regions with less snow influence. That's what we see. What we see as this spatial pattern. The other question that we might ask is how sensitivity of storage, the discharge to a storage changes in each catchment across different flow regimes. So here I have 4 examples of catchments from different regions. And what we generally see is that storage sensitivity decreases from low flow to high flows, but with very different patterns across catchments. So these 4 examples show that although in all catchments we have storage sensitivity that is decreased from low flow to high flow, but the shape is very different. The ranges are very different depending on catchment attributes. For instance, let's focus on catchment A and B. Catchment A is in Florida region. And catchment B, both of them have almost the same aridity index, but catchment A is in Florida region. It's generally rain dominated. Catchment B is northern Canada. It's highly snow dominated. You may see that. So just to mention that all of these plots, y-axis shows sensitivity. I hope you see that. And the x-axis shows the percentile of discharge, or like as we move from 0 low flow to high flow, which is 100%. What we see from catchment A and B, the shape of these are different. The A is nonlinear, B is almost linear. Also, the ranges are very different. In catchment A, for low flow to high flow, the sensitivity changes almost 1,000 units. But for the catchment B, which is a snow-dominated region, we have almost 10 to minus 1 change, roughly. So what we can learn from these is basically future of this study. We might be able to learn how these shapes are related to maybe connectivity of groundwater. We see some threshold-like behaviors in some of the catchments that might represent some changes in behavior in groundwater that we might have. That's the future of this study. Also, we are going to like extend the study area in near future. We're going to see how we can evaluate the sensitivity function across like ungauged basins, and also if we to see if we can like have some indices that can be evaluated using just a some static catchment attributes to have some rough estimations of catchment sensitivity. And but the general message, which is also compatible with the title of this session, is that we can use machine learning, AI applications to learn knowledge from data without having any assumption on the functional form. As long as we have some general valid physical questions, we are able to use deep learning models, AI models, to learn from data. And this is something that is useful in the age of data, that we have lots of data that we don't know what is going on behind the scenes. And yeah, thank you for your listening.
We had a couple minutes for questions. If you want to go to Mike.
Thank you very much. That was really, really interesting. So I have a quick question. For this LSTM, how long did it take for you to perform it, train it, test it, and validate at the scale that you're looking at? Are you using all the data in one framework, or are you preparing or generating LSTM across, in different catchments for catchment-specific model? Yes.
So I don't know if I really understood your question, but I didn't really go over the details, but we first make one general LSTM model for all the catchments, okay, and then fine-tune it for each single catchment. So using like supercomputers that we had, it took almost 1 week to evaluate this model across all the catchments that we have. Okay. But I believe it can be even more efficient if we use like better parallel processing. Did I answer your question, or?
Absolutely. Great work. Thank you so much.
Yeah.
Thank you very much for your great work. I have some recommendation and one question. The recommendation is that the LSTM model work well, but your evaluation criteria is based on correlation. I recommend that add some statistical criteria such as error-based, such as root-mean square or mean absolute percentage, to better understand the performance of the model. You know that the correlation-based, perhaps your output have a large amount of the scatter, but biasly it may perhaps shows the higher Nash coefficient. Another thing is that I recommend to compare results with any conceptual model or another AI techniques to confirm, to support that, yes, I developed a model that outperform other traditional methods.
Yeah.
And another thing that I would like to recommend in parallel to the question of the Professor Monire, there's large number of the catchment in your study. And as you say, it takes long amount of time to perform each model for each catchment. Nowadays, some multi-output models are generated and are available. There are several packages, and perhaps you can use this model to save your time. At the same time, you can predict the multi-output variables. Perhaps that the neighbor catchment perhaps have some correlation together, and perhaps it improve your performance. And my question is that what is about how you prevent the course of dimensionality and overfitting in your model?
You mean how did we prevent overfitting?
Oh, yeah.
Yeah, so we have different criteria. So one criteria is just testing the model as we normally do in all the applications of AI. Like this is what I'm showing here is just test NSE. The other thing is just using different like regularization techniques that I didn't name them here. But for instance, I used L1, like L1 on L1 regularization on the smooth, and also smoothness on these kernels that you see here. Let me bring the kernels again. So you see the kernel behavior. So we expect the kernel behavior to be somehow smooth. So I did have some smoothness penalties as well as L1 penalties. And but in future, we are going to have like ungauge basin analysis, and that would be like the major like test of this method. If we are able to represent like catch ungauge basins like with like acceptable accuracy, that kind of shows that it's not like overtrained. But for this, for a study that I represented here, is just we use test NSE and other regularizations like dropout and stuff like that to make sure everything is going well. Yeah.
Our next speaker is going to be Javad Rahmani, who's going to tell us about runoff dynamics. Are you on PDF or?
So.
How does it work?
Oh yeah, just 1 second. Show the screen.
Oh,
So the green is forward and then red is back. And if you want to use the pointer, it's up.
Oh, sure. Okay. Hi everyone. I'm Javad Rahmani. I'm presenting our research on interannual variation runoff generation between pothole-dominated catchments in peri-pothole region. And peri-pothole region contains between 5 to 8 billion depressional storages. These storages are called potholes, and they store water and disconnect upstream area from downstream river network until they are filled. When they are filled, they connect to the downstream river network, and they start to contribute to the flow generation. This process is called fill and spill and is essential for flood mitigation, drought resilience, water purification, carbon sequestration, biodiversity, and lots of other ecosystem services that all of them are highly influenced by interannual variability of water balance and also runoff generation in catchments. So it is critical for us to understand how interannual variation of water runoff generation occurs in these areas. Bihlo framework is one of the widely used framework for interannual variation of input, for analyzing interannual variation of input water to the catchment, it states that in a long-term state, precipitation is divided between evapotranspiration and river discharge based on available water and available energy in the system. Bihlo used RDT index to show available energy with potential evapotranspiration and available water in the catchment with precipitation. And later, people use this framework for interannual variation, not for long-term scale analysis. And they use it for interannual variation of evapotranspiration ratio generation in a catchment or runoff ratio in a catchment in a single catchment. In this study, we want to check that is Bihlo framework is valid in wetland-dominated catchments or not, because we know that potholes highly affect runoff generation in pothole-dominated catchments. To do that, initially we check potential drivers of runoff ratio, their partial correlation and full correlation. The first one is the aridity, the first variable. Following Bihlo framework, we use aridity, we check its correlation with runoff ratio. Then we check maximum inundated wetland area, MIWA, extracted from satellite information, satellite data, from Landsat data, to show the potential behavior of the potholes in generating flow generation in peri-pothole region. Also, we check extreme rainfall, snow fraction, snow persistence, and lagged effect of aridity in runoff generation. As we can see in the right section, most of the hydrological process, such as inundation and stream flow, occurs between March and June in peri-pothole region, so these months are very important for us. Based on partial correlation analysis, in the first step, we check that whether aridity, the Bihlo framework, or inundation is the main driver, and based on that, we classified all 109 study catchments that we have in this study into 4 groups. The first group is fill spill dominated, those that inundation is the main driver, and aridity correlation, partial correlation with runoff ratio is not important. Aridity dominated, those that aridity is important. Jointly dominated, those that both of them have partial correlation larger than 0.5, and neither dominated, none of the inundation and aridity can drive runoff generation in the in catchments. Also, we check the inundation runoff ratio in a relationship by fitting a 3-parameter power law equation to a scatter plot of runoff ratio and inundation. And the parameter B value is very important for us, because any deviation from B equals to 1 shows a nonlinear response between inundation and runoff ratio relationship. Also, it is important for us to know that what properties of catchments drives these B value in each catchment. So we have conducted a spatial correlation analysis between B values and catchment-specific properties, such as long-term inundation, riparian wetland inundation, geographically isolated wetland inundation, long-term climatic variables, land use, land cover, soil properties, and other specific catchment-specific properties. Our result shows that, as we can see, the relation between MIWA, inundation, and runoff ratio in these 3 example catchments is highly better and stronger than those relations between aridity and runoff ratio, which was introduced by the Bihlo framework. So we can see that inundation is doing something. To have a better visualization of all catchments correlation, we generated the full correlation between inundation and runoff ratio, and also between aridity and runoff ratio, and also the partial correlation maps of inundation and runoff ratio while adjusting the effect of aridity, and also partial correlation of aridity and runoff ratio. All together shows that inundation exceeds aridity index in explaining interannual variation of runoff ratio in peri-pothole region, at least in most of the catchments. Our classification shows that out of 109 catchments, 76, more than 70% of them, are classified as fill spill dominated. It shows that inundation is the stronger driver of runoff ratio compared to climate variables. In fill spill dominated catchments, long-term inundation area is significantly larger than those than rest of the catchments. It is 3.5% of area of catchments versus 1.33% of the area of the catchments. This higher storage potential causes that runoff ratio, long-term runoff ratio in fill spill dominated catchments be strongly and significantly lower than rest of the catchments, as we can see in the box plot. We also checked other potential drivers of runoff ratio, such as extreme rainfall, previous year aridity, snow fraction, and snow persistence. Our analysis shows that extreme rainfall and snow fractions do not have any significant correlation with runoff ratio, but previous year aridity and snow persistence strongly in some of the catchments, mostly those in US part of the prairie, are strongly correlated with the runoff generation in the catchments. To have better analysis to see that how inundation mediate this effect, we also conducted partial correlation analysis, and we see that when we adjust the effect of inundation, the partial correlation between previous year aridity and runoff ratio decreases. But when we adjust for the effect of previous year aridity, the partial correlation between inundation and runoff ratio does not drop that much. So it shows that the same pattern happens for snow persistence, and all of them together shows that previous year aridity and snow persistence control runoff generation in prairie plateau region by influencing on inundation of the catchments. Also, curve fitting analysis shows that the B values in 64 catchments, fill spill dominated catchments, out of 76 fill spill dominated catchments, have B value larger than 1.25, which shows that they have an exponential behavior. Here in this scatter plot, we can see a catchment in North Dakota with B value close to 8, and we can see that how exponential behavior occurs in these catchments, and also how threshold-like behavior we can see that in the first section of this threshold behavior, filling is happening, filling phase is happening, and connectivity only is increasing. There is no runoff generation, no significant generation runoff. But in the second part, when all passes are connected, a spillage started, and any increase in inundation will significantly and exponentially increase spillage in the catchment. It shows that how important is that first 3% of the inundation. And imagine that if this percent will drain or will lose them in the catchment, when we have an input water, it directly starts from the exponential part, and it generates floods and extreme runoff in the catchment. Also, analysis of drivers of B value shows that geographically isolated wetlands inundation, long-term inundation, is the main driver of this B value. We can see the fitted curve for those inundated fill spill dominated catchments with R square larger than 0.5 in this example, and catchment A, which has a linear behavior, B equals 1.07, its geographically isolated area is less than 1% catchment. But for catchment B, with a B value close to 5 in North Dakota, we can see that geographically isolated wetland is 3.2% of the area of the catchment. And we can see the distribution of the potholes in catchment B compared to catchment A, that it doesn't have that much inundation in the figure. And the conclusions is that Bihlo framework does not work in prairie pothole region. Instead, wetland inundation strongly controls runoff generation in the catchments, and also snow persistence and previous year aridity play a secondary role through influencing on inundation in the catchments. So years with high snow persistence and low previous year aridity should be considered high flood risk years in the prairie pothole region. Particularly in spring, we should expect that if there is any significant rainfall in the catchment is ready to generate high flow in the area. Also, there is an exponential relationship between inundation and runoff ratio in the majority of the catchments, that if we lose some of the inundation potholes due to any reason, the drainage by farmers or anything else, this exponential behavior can shift from exponential to a linear, which can increase flood susceptibility in the region. Thank you very much.
We have lots of time for questions. So does anyone have any questions? I have a question.
Sure.
Okay. So I have two little questions. I'll ask them at the same time. The first one is the Bihlo curve that you showed very early on. Is that an empirical, semi-empirical, or is that a theoretical prediction? And the second one is you showed this equation with the B parameter that controls the nonlinearity. Historically, in this problem, has the problem been thought to be linear or nonlinear? And then I think you mentioned this a little bit in your talk, but could you point out what are some of the specific physical mechanisms that can generate the nonlinearity?
If I understand your question correctly, you wanted to say that what drives this exponential behavior?
So what's the physical mechanism?
Okay. The physical mechanism is Phillips-Build mechanism. As I explained, this Phillips-Build mechanism shows that the upper stream of the potholes does not contribute to fluid generation until these potholes are filled. When they are filled, they start to spill and connect to the downstream river network. So this behavior causes that, and also the spatial distribution of these small potholes and this Phillips-Build process, this spatial distribution causes that all together in the catchment scale behavior shows this nonlinear and exponential behavior. I think
My other question was the Bihlo curve. Is that a theoretically derived curve or is that empirical?
It's empirical, but it has been used widely in hydrology, especially in line-term analysis and spatial analysis. But later people started to use it for temporal analysis in single catchments.
Right. Which does not work as well.
In prairie it doesn't work, but around the world they have used it and it works.
Great. Thank you very much.
No worries.
Our next speaker will be Fadli Atarita, who's going to be talking about remote sensing.
It's a while. Yes. Okay. So this is the web.
That's the point.
Okay. Hi, everyone. Thank you for being here. My name is Fadli. I'm a graduate student from Queens. And before I begin, I just want to mention that there is no AI or machine learning in this presentation, so sorry to disappoint you. But yeah, this presentation is about our hyperspectral remote sensing simulator called HiCMU. And I'll give a brief introduction about hyperspectral imaging itself, and then the motivation behind our study. And then I'll explain what HiCMU is and how it works and its potential applications, and then I'll end with some conclusions. So what is hyperspectral imaging? So it is defined as the acquisition of images in hundreds of registered spectral band, continuous spectral bands, such as that for each pixel, a radiance or a reflectance spectrum can be derived. So here in the middle of the screen, we have what is commonly referred to as a hyperspectral data cube. It has two spatial dimensions and one spectral dimension. Okay. And if we take out a pixel from this data cube and then plot the values, then we'll get what is called a radiance or a reflectance spectrum. This is useful because each material has a unique reflectance spectrum. And if we have enough data points, we can do some analysis and determine what the pixel represents in real life, what the material is. And if you put a hyperspectral sensor on top of a remote sensing platform, such as a drone, an aircraft. Then we have a hyperscalar remote sensing system. And this is good because then we can take images of a wide area and then determine what the surface material is just by analyzing these images. And why hyperspacial imaging compared to the other optical techniques such as RGB cameras or multispectral cameras? So RGB cameras, like the ones on your phone, it takes pictures in RGB. Basically, the pictures have 3 layers in red, green, and blue. And if you plot the values, you'll get something like this, probably a linear interpolation. And if you have more resolution, then you'll get a more accurate representation of the reflectance spectrum. And this, with some analysis, we can classify the pixel as like what the material of the pixel is and then differentiate between all the pixels in the image. So this is very useful and it has a lot of potential applications. Such as here, I'm going to show 2. One on the left is for algal bloom monitoring by Olivetti et al. 2023 and for mineral mapping by Graham et al. 2018. But it has a lot more applications, such as for alteration mapping, vegetation mapping, urban planning, carbon detection, and lots of applications. And in the last 2 decades, hyperspacial remote sensing field has been becoming mainstream, and this is a data by Engineering Village showing there is an increasing trend in the number of publications published in in hyperspectral remote sensing in the last decade. And combine this fact with the facts that right now we have more than 20 currently operating or planned missions, and that we have more than 30 commercially available sensors that are suitable with drones. And these raise questions. If you want to do hyperspectral remote sensing survey for your applications with so many options to choose from, so many datasets available, how do you design your survey and how do you optimize your parameters? And one of the solutions for this is by using a simulator. Hyperspectral simulators, there have been quite a few of them developed over the years. And what it does is it allows for the adaptation and optimization of sensor and platform and observation conditions. And here in the table, there are listed some of those simulators, but there are a few more that are not listed in this table. And some of these simulators are commercial, and some others were designed specifically in the support of a mission. And the rest, for various reasons, are not easily accessible. That is why we think that there's a need for a readily accessible HRS simulator. And now I'll introduce you to HiSimu. It is a starting framework of an open source, modular, sensor and platform independent simulator. It's written in Python, so it's open source, and it's for parallelization. What it does is basically, if you have ground truth, which is the representation of the surface material, HiSimu will take that ground truth and transform it into a set at sensor radiance data cube. So basically what the sensor sees from at an altitude. The benefits of this are 1, to optimize survey design and planning, and 2, it can be, because HiSimu can generate synthetic datasets, those datasets with varying parameters can be used as training datasets for prediction algorithm, as we will see a bit later in the presentation. So how it works is basically the first step. HiSimu starts with a ground truth map, which is derived from a surface distribution map combined with spectral dataset and DDEM, and then put it into the first module of HiSimu. And HiSimu will generate full resolution surface reflectance data cube. And then this full resolution data cube will be transformed into full resolution radiance data cube that has atmospheric parameters included in it. And the next step is to downsample the full resolution data cube to sensor resolution, because we're talking about a remote sensing system, so there is a difference in the resolution at the surface and at an altitude. So for the first module, the ground truth builder, what it does is basically it takes the surface distribution map, the distribution of the material on the surface, and combine that with the spectral datasets. So here we have random mineral spectra from the USGS Spectral Library. And then HiSimu will take these inputs and create a full resolution surface reflectance data cube. And for the next module, here is a graphic of how the solar irradiance comes from the sun, reflected off the surface, and then to the sensor. Basically, to calculate the radiance, we need incidence angle, which depends on the surface normal vector. That means if we have a non-flat DEM, we have to correct this angle of incidence. And the way HiSimu does it is by calculating the sun position for each pixel, and then calculating the slope and aspect for the from the DEM, and then using a formula correct the solar and view incidence angle radiance. And what this does is here we can see the difference. On the left is an image generated without correcting the solar the incidence angle, and on the right is an image generated by correcting the solar angle. So basically, we can see the effect of shades basically on the image, and it will generate a more realistic image, for a more realistic synthetic image compared to if you don't correct the solar angle. The next module is for radiative transfer modeling. So basically, RTM is a numerical model of how the energy, the solar irradiance, travels through the atmosphere, reflected off of the surface and back to the sensor. And here HiSimu integrates two open source RTMs, 6S and Libratron, and there is also an option to not use any RTM. And each one of these has its own advantages and disadvantages, as you can see on the slide. And on the bottom, we have 3 images, RGB images, that were generated using each of these RTM. And practically, visually, you cannot see any differences in these images. But if we take 1 pixel out of all of these images and plot the radiance spectrum, we see some degree of differences between all these images. And basically, there is no right option here. It all depends on your applications. So some RTM has greater control in the atmospheric parameters, but can be quite difficult to set up or can take a longer time. So yeah, it basically depends on your applications and what you want to do. The last module is for the spatial resampling. We have HiSimu has 2 options: simplified PSF, which works if you have a limited info about the sensor and platform parameters, and it works for all sensor types. While the other one is the SR2 function, which is an integrated function by Namdar et al. 2023. It applies a more detailed platform and sensor parameters, and it is suitable for push broom sensors. Here you can see the difference of these two functions. And I'll go through some examples that you can use HiSimu for. The first one is for mineral exploration. Here we have the ground truth, and here we have some of the parameters that go into HiSimu. And here is the RGB radiance image. And if we zoom in into these images, we see how that we lose so much details because it is a remote sensing system. So what we can do is basically we can change the simulation parameter and see which parameter is more important. And doing sensitivity studies, we can determine the optimum parameters that we need for our specific applications. And the next example is for carbon detection. This is a project that we're doing with Metaspectral. Basically, because you can put atmospheric gas parameters in the RTM, we can create synthetic data sets with using varied atmospheric gases concentration in the atmosphere and generate synthetic data sets to train prediction algorithm. Here, one example that we did, this is a randomly generated methane concentration map in the atmosphere. And we do simulations with this methane map to generate this image, this radiant image. And because this is a forward model, Of course, we can also do an inverse modeling of this image. And using an inverse model and a meta-index analysis, we can, this is the result. So basically, this is the inverse result of our synthetic datasets. We can see a high correlation between the inverse result and the input. So we think using a lot of synthetic datasets that are generated this way, we can train a prediction algorithm to detect gaseous concentration in the atmosphere using satellite imagery. And the last example is for algal bloom monitoring. This is a study by Bone et al. 2025. I'm not gonna go into details about this, but bottom line, so basically the left picture is the algal bloom forecast nowcast model from Lake Erie, from the Gloria dataset, and this is the simulated radiance image. What this study found was that HiCMU was able to evaluate the abilities of different satellite sensors to delineate features in algal bloom models. So in conclusions, hyperspectral remote sensing is becoming mainstream, and there is a need for an open source simulator. And HiCMU is that open source simulator that we are developing. And it can be used for sensitivity studies, for survey optimization, and that we've shown some examples. But applications in other fields are very possible with HiCMU. That's it. Thank you. I want to thank our partners for this project. And yeah, thank you.
We have time for a couple of questions. Any questions? Please.
Hi. I was wondering if there's a minimum requirement for the DEM, like for the resolution, to be able to do something with that.
So it has to be at least at the same resolution of the sensor resolution, but better if it's of a higher resolution than the sensor resolution. Yeah.
Thank you.
Okay.
Other questions? Good. Thank you, Pro.
Thank you.
Okay, and our final speaker for this afternoon is going to be Colleen Henschel, who will talk about passive microwave satellite retrievals. Are you PowerPoint?
This is next and that's back. Yeah, okay. The screen looks,
Okay, sorry.
okay, great. Okay, hi everyone. My name is Colleen Henschel. I'm a PhD student at Dalhousie University in the Department of Physics and Atmospheric Science. I'm working under the supervision of Tom Duck. And my PhD project has been focused on using artificial neural network architectures to perform passive microwave satellite retrievals over the Arctic and Antarctic regions. And this talk specifically is focused on the work that I've done for taking an image from the satellite and producing an output image of the retrieved geophysical parameters. So this satellite that you see imaged here is the Suomi NPP satellite. It's part of the Joint Polar Satellite System, and it's in sun-synchronous orbit. It makes a full rotation around the Earth roughly every hour and a half. And it turns around in its orbit around the 80-degree latitude line. So there's a high concentration of measurements at the North and South Pole. And the instrument that I'm using is the Advanced Technology Microwave Sounder, or ATMS. It's a cross-track instrument that measures from negative 65 degrees zenith angle to 65 degrees zenith angle. And what you get is a swath, like you see in the bottom left here. That's just one channel of the swath. It's 96 pixels across, and then typically they package them in 180 rows. So that's 180 scans. And the idea is to take a swath image that has 22 channels and then produce a same-sized image with all of the retrieval parameters as different channels of that image. So just a little bit of background about the ATMS. The blue dots in this figure show the locations of the channels for ATMS. So this instrument was designed for weather forecasting purposes, for temperature sensing and water vapor sensing in the atmosphere. So channels 18 to 22 are all located under the strong water vapor absorption line at centered at 183.3 gigahertz. And then channels 3 to 15 are the atmospheric temperature profile sensing channels in the V-band region, so the oxygen absorption lines. And they're sensitive to different heights within the atmosphere. So I have a plot here that's showing the weighting function. So that's derivative of transmittance with respect to altitude. That shows the region that each channel is sensitive to for a particular atmospheric state. So you can see for like the yellow line there for channel 15, it peaks at about 40 degrees above the surface. So that channel is really good for getting the high altitude temperatures. And then I also have a plot showing the weighting functions for the other channels. The water vapor channels are sensitive much closer to the surface. I am making an attempt to retrieve water vapor profiles as well, but they're a little bit worse than the temperature profiles because that information isn't really stored in those brightness temperature measurements. So the first step of this project was actually to just look at a single pixel where I take the 22 brightness temperature measurements and the satellite zenith angle for a single pixel, and then retrieve all of the parameters of interest. So the inputs, as I said, are those 22 channels and satellite zenith angle. The outputs are the temperature and humidity profile values, along with the total column integrated water vapor. And then the surface parameters that I'm retrieving are the effective emissivity and the effective surface temperature, which is also known as the emitting layer temperature, for all of the frequencies available. And then I'm also making an attempt at retrieving the 2-meter air temperature and specific humidity. The channels aren't really sensitive to 2 meters above the surface, but there's a lot of measurements for those values, so they're easy to validate. And the information is stored within the temperature profiles and the surface parameters. It's like interpolated in between. So for this talk, I'm just going to be validating the high frequency emitting layer temperature, so 183.3 gigahertz. And I'm comparing it to ground-based measurements of upwelling and downwelling long-wave radiation, which I'm calculating the skin temperature for. Skin temperature is just the temperature of the very top layer of the surface. And in this equation, LW up is upwelling long-wave radiation, LW down, downwelling long-wave radiation. Epsilon S is the snow emissivity, which is being set to 0.985 in this case, and then sigma is just the Stefan-Boltzmann constant. And these maps are showing the location of the stations that I'm using. They're from the Baseline Surface Radiation Network, or BSRN, and the Global Monitoring Laboratory, GML. And I'm also comparing to the Mosaic Expedition dataset, which was a year-long ship-based campaign where an icebreaker was frozen into the sea ice. They had 4 different radiation towers taking measurements conveniently roughly at the resolution of the ATMS high-frequency channels. So where possible, the Mosaic dataset was averaged for comparison. So first, we're going to look at the performance of just that single pixel retrieval. This is just showing the correlation coefficients for each of the different data sets. The amount of data in each of these data sets varies somewhere between like 6,000 to 20,000 points. For the most part, and I have them ordered here from low latitude to high latitude, and then there's the black line, and then it's the Antarctic stations from low latitude to high latitude. So the first station in the Netherlands, this cab station there, does quite bad compared to the ERA5 performance compared to the same data set. But other than that one, they're usually within, 100th or 200ths for the correlation coefficients. And then if we look at the mean bias of the data set, you can see ERA5 has a slightly positive mean bias in blue points. Sorry if these are hard to see. And then the neural net actually tends to have a slightly negative mean bias. It is worth noting, though, that because I'm comparing 183 gigahertz emitting layer temperature to skin temperature, they're not exactly one-to-one because 183 gigahertz may penetrate around like a centimeter into the surface. So there's like a slight difference in what I'm comparing, and then also just the spatial averaging. Like I'm looking at a footprint of 30 kilometers and comparing to per geometer measurements that are on the order of meters. But I'm pretty happy that the comparison of the single pixel neural net to ERA5 is about the same. If you take the average of all of these data points, I think ERA5 was about 0.8 overall bias, and then the ANN retrieval was like negative 0.5 or something like that. So it's not like really obvious that one of them is outperforming except for that low latitude station. And then these are the RMSDs. Generally, ERA5 is a little bit lower compared to the neural net retrieval, but the ANN performs quite well. So yeah, moving on to the image retrieval. So the architecture that I'm presenting here is the SWIN UNet. I also tried a typical UNet and then just SWIN transformer without skip connections, but the SWIN UNet performed the best, so that's the model that I'm presenting. We already saw a UNet presentation in this talk, so I'm not going to go through a lot of detail, but it's basically the same idea. Instead of just convolutional layers, you're adding SWIN transformers, which stands for shift transformer layers. So it uses self-attention to try to look at the relationship between different patches within the image. And then you downscale the image for feature extraction and then upscale, and then you have skip connections in between. So then if we look at the comparison of the SWIN UNet and how it performs to the single pixel retrieval and also to ERA5, you can see that the single pixel and the SWIN UNet are basically identical in terms of correlation coefficients. You know, the biggest difference there is, I haven't looked at this recently. I think it's like 0.01, sorry. Like they're very, very close to the same value. And then the mean bias, the SWIN UNet actually seems to be a little bit closer to 0 in terms of mean bias, but there are some stations, the Showa station in Antarctica, that first one after the black line, is quite low negative bias, but there's no like very noticeable difference in performance compared to the single pixel retrieval. And then if we look at the RMSD again, sometimes the single pixel is a bit higher and sometimes it's a bit lower in terms of how far away they are from the measurements, but they're very similar. So yeah, basically what I've seen is they're about the same in terms of quality of retrieval. So then we'll just look at some swaths to see how they look spatially. So the top row is skin temperature, the bottom row is integrated water vapor. And hopefully you can see that the single pixel retrieval on the far right is a little bit pixelated, and you can see a little bit of discontinuity compared to the middle column, which is the SWIN UNet retrieval. But generally the two have the same structure, with the SWIN UNet being a little bit smoothed out, maybe a little bit of structure is lost there, but they are overall in magnitude about the same and in structure about the same. And then just for comparison, I also have ERA5 on the far left, where there's a little bit of structure difference, but the smoothness is about the same as the SWIN UNet. And then I have some emissivities to show. The top row here is the SWIN UNet retrieval, and then the bottom is the single pixel multi-layer perceptron model. And you can see that they're basically the same. You can see a little bit more pixelatedness in the single pixel retrieval again, but the overall values are basically the same. And then to talk about the temperature profiles, I have ERA5 in the top, I think single pixel in the middle, and then SWIN UNet in the bottom. And if you don't squint, or if you squint or look from far away, they basically look like the same picture. ERA5, you can see there's like a bar in between 2018 and 2019. That's just green. That's just like missing profile values. They're all just being set to 255 Kelvin. And then in the bottom row, there's some white lines there. Those are locations where I didn't have a full 96 by 96 image to retrieve with the image retrieval, so then I just left them as missing data. And then if I include the radiosonde profile measurements, you can see roughly the same structure there as well instead of ERA 5. And then this last slide is just showing the specific humidity profiles as well. And then there's, sorry, let me just go back one. The white there is just anything that was less than 10 to the minus 6 is going to be white. So that's just the SWIN-UNet retrieving really small values for the upper atmosphere. Yeah, and then just for wrapping up for discussion, I did test also UNet architecture and SWIN transformer without skip connections, but the SWIN-UNet performed the best, which is why I'm presenting that here. The results that I see between single pixel and SWIN-UNet are very similar in terms of accuracy compared to ground-based stations. So it seems like it works pretty well, but it's hard to make an argument that it's like better by adding the spatial information. Main advantage of the SWIN-UNet that I can see is that it's a little bit faster. To retrieve a single swath, it's about 5 times faster than using the single pixel retrieval. Main disadvantage is it only works if you have a full 96 by 96 image. So if you have like sub-swaths where there's missing data on either side, you can't get a retrieval. And in that case, the single pixel is better. There's possibility for expanding this method. You could do some gap filling with it, where you mask the input image and try to get it to extrapolate the output image or interpolate. And then you could also try to do like a super resolution retrieval using the same architecture. Something I forgot to say earlier that is very important. I am training this on simulated training data. So I'm using RTOV, which is a fast radiative transfer model, and I'm simulating brightness temperatures. So I know what the surface and atmospheric states are to create the training data. Yeah, so just acknowledgements. There's a lot of open source data and products available to create this model, and I'm funded by NSERC. So thank you very much for sticking around.
We have time for a couple of questions. Any questions?
Yeah, I was just puzzled how you managed to separate the radiance from 2-meter air from the radiance from the ground. So how do you extract a 2-meter temperature?
So because I'm doing simulated training data, I'm passing in to RTOV the 2-meter air temperature and the temperature profiles, which I'm starting with ERA 5 as input values to RTOV. And then the skin temperature is sort of ERA 5, but then with some variance because there's penetration depth. So I just like take ERA 5 values, add a little bit of noise to it, simulate brightness temperatures, and then the model just figures it out. I didn't show any validation of the 2-meter air temperature and the humidity. They look similar in quality to ERA 5 at the different stations that I've looked at. And I guess like the model is able to interpolate it.
Okay. You're looking at multiple wavelengths, right?
Yeah, there's 22 channels from 23.8 to 183.3 gigahertz.
Okay, yeah.
Yeah, it's cool.
I'm just surprised.
Other questions? I have some, but since we're over time, I'll ask those offline.
Okay.
Thank you very much again, and thanks to all the speakers. And this concludes our session. Thank you for coming.
Yeah, it was just a single picture.
Yeah. So, that's right. But you did look at it.
Yeah. These are like the temperature profiles. The black is the radius one measurements.